recording. Take out your favorite red writing utensil. Here are the answers. Hold those fingers so the people at home can see me. For people watching at home, howdy. Homework 60-3. Here we go. Number 1. The answer is 124 pi over 5. Number 1. First of all, let me double check. The computer has scrambled these problems before. Is it y equals radical x, y equals 0, x equals 1, x equals 4? Good, pretty good. Okay. So it's 124 pi over 5. If you didn't have that, write it in. Number 2, 4 pi over 5. Number 3, 8 pi. And number 4, 4 pi over 5. The tricks for number 3 and number 4 is that you have to lower the graphs down to the x-axis. That means you have to change the formula. Alrighty. First of all, repeats. Questions? Either those you want to see worked, dissected.
Wait, it was number 2, 4 pi over 5.
4 pi over 5, right. Don't want to see any of those? Yeah, you can blow it over, just keep it in the cool area.
You want me to?
No, we're good. Okay, we're good. And you were.
I was at confession.
Oh, gotcha, gotcha. That's a good thought. Questions?
Yes.
So, sorry.
You gotta be kidding me.
Mr.
Go
Carter,
ahead.
I just have a question for you more. You just switched the X's and Y's.
That one you don't have to switch the x's and y's.
Disgusting.
Number 3, you notice it's the floor is not the x-axis, it's y equals 2.
Leave it out on the desk.
You have to lower the main function by 2, so it becomes y equals x squared. Then do the shells.
So gross.
Okay, gentlemen, we're in class. Tune in. Any questions? 1, 2, 3, or 4? Yeah. Number 3, definitely. Y equals x squared plus 2, and then the lines bounding it are y equals 2, x equals 2. Here's what it looks like. X squared plus 2 starts 2 spaces up. Don't start chit-chatting. Find something to work on. We're in calculus class now. You start here, and it's a normal problem. Over 1, up 1, over 2, up 4. 2, 3, 7. Over 1, up 1, over 2, up 4, down, I can still hear you talking. They wanted to vary a y equals 2 and x equals 2. So this little region, they wanted to spin around the y-axis. We have never done a problem where it's hovering off the ground, so to speak. And in a sense, we never will. How do you spin this thing around the y-axis? You don't. Because if you try to use discs, what would be the problem of using discs on this thing? Like you pick any point along the parabola and spin it. What would be the problem of using discs? Maybe see it visually. What volume would that capture? Like if I just picked a random point here and spun it, make a disc, what volume would that capture? I want this thing, which will make it kind of an egg cup. Will the discs do that? Jack?
No.
No. What shape would it make? Like where would it give you the volume for it?
Inside.
The inside, the bullet shape, which is what we do not want. We want the shape of the outside. So if you try discs, you get the wrong answer altogether. Let's try this. Discs don't work because they're capturing the wrong portion. Try shells. Shells fall. Here's the phantom version on the other side. That looks good. But question, what's the problem with that?
Oh, I was just going to say, I did discs on this problem and got the right answer, so.
That is insanely lucky. The reason? this particular exact shape, the outside volume and the inside volume are the same. That is, will happen like 1 out of 10,000 chances. So don't rely on that. Yeah.
Let's say like that was on the test and we did discs and we got.
I
the
would
right
take off
answer.
major points because that's a complete coincidence. And if I had even changed this to 2x squared, totally wrong. So it's a little like if I had asked somebody to do a calculus problem and the answer was 6, and somebody put the answer 6, and the work they showed was I threw a 6-sided die and it came up 6, I would not give you points for that.
Why?
It's called being lucky. It's called not knowing how to do the problem, but being lucky. Does that make sense? I want to make sure everybody knows how to do shells and not just discs. Okay, not everything can be done with discs. This, let's see who remembers this from 2 days ago. What's the problem with using shells? Shells do capture the outside, which we want. But if you draw a shell, what's the problem? You should see an immediate visual problem. In your notes, yeah. They fall to the ground. If I try this, it falls all the way down. You're gonna have a shell that's way too tall. Does that make sense? You're gonna have a really, really tall egg cup, way taller than you need. Can you fix it? Yeah, if you're clever. You can find the volume of the cylinder that's underneath the cup and subtract it. But there's an easier way. Physically take this graph and move it. How far will we have to move it down in order to get to the floor? 2. Move it down 2. Can somebody tell me how to do that? It's actually not too tough.
Subtract.
Say again?
Subtract.
Subtract from the input or output?
From the, well, you'd like just, it would just be x squared, right?
Correct. In other words, don't subtract from the input. Don't do x minus 2 parentheses squared. That would move it to the right 2 spaces. So yeah, this moves it down 2. It's y equals x squared. So you're now, the new transformed graph looks like this. It's a plain old parabola, vertex at 0, 0. Ah, thank you. Yeah, gentlemen, let's not start
They were
chatting.
speaking
Okay, I'm tuning in. We're doing the worksheet 1 through 4. Is there a problem?
We just want Noah. That's all.
Okay. Here's the thing we want to spin around the y-axis. Now we can do it. Refresh my memory. Pete, what is the volume of a shell? A single shell. What's the formula? Disk is pi r squared h. What's a shell?
Is that pi?
Starts with something else.
2.
2 pi.
H.
Close. Want something right before that.
RH.
Don't whisper, please. R, H. One last letter.
T.
T. 2 pi RHT. Memorize that. That's the volume of a shell. Radius, height, thickness. So if you pick any old shell to drop down, the volume of that shell is 2 pi RHT, which means it's 2 times pi times something times something times something. Can somebody please tell me what the somethings are? Polly, tell me out. In this particular picture, what's the radius? It's got to be x, y, dx, or dy. X, correct. What's the height? Sometimes. It's got to be x, y, dx, or dy. Y. And what about the thickness? dx. Why not dy? That's correct, by the way. I'm sorry? Yeah, it's going in the x direction. Why not regular x instead of dx? Yeah, it's really, really thin. It's almost zero, but not quite. This is what we're about to integrate. So the volume of a single disk, shell, let me just rewrite this neatly. 2 pi x y dx. Anybody see a problem with that?
The Y.
The y. What's the cure for that? Go.
You can, well, we have Y equals X squared now. so-
Right. This one we threw out. Here's the new function. I'm going to replace this with x squared. Give me the new formula now.
Oh, 2 pi X cubed.
X cubed dx.
dx.
Excellent. Now we're ready to go. How do you get the entire volume? Max.
I take the integral.
Integral, correct. Do you think we're going to go, we're going to add up the x's or the y's? Here's your formula. Are we going to do boundaries with x or boundaries with y's? In other words, are we going to go
Oh.
from 0 to 2 or 0 to 4?
0 to 4.
Explain.
Cause
There's something in the formula that tells you.
y equals x squared.
That's the original equation. Here's the volume of a shell. Look at that. What's the only variable they're using at all?
X.
X. So whenever they have this dx at the end, that's the letter you use.
Okay.
If it's dy, then you would have used the 0 to 4. But in this case, it's what? From what to what?
0 to 2.
Exactly. From 0 to 2. X equals 0 to x equals 2. Of 2 pi x cubed dx. I'm going to pull the 2 pi out front. The integral from 0 to 2 of x cubed dx. Let me stop there and make sure everybody understands what we just did. There are 3 steps we did so far. This thing was floating off the ground, which we cannot do. If you tried shells, the shells fall all the way to the floor, and it would make the volume way too big. The shells are too tall. You have to physically lower this graph so that it's sitting on the floor. We did. Now do shells. And we got 2 pi r h t. Replace the y because it's the oddball. And we got this. So how do you calculate that? Yeah, question.
I was just wondering, so how did you get the x equals 2 being down and then I'm just confused.
Oh, the original one, this equation is y equals x squared plus 2.
Yeah.
And if you look at the picture, they stopped here at a height of 2. And if I can't do shells because the shells fall all the way down, it's too tall. So we're going to manually lower this by 2 spaces and spin that. And that'll still give it, yeah. Because if I spun this, like if I just did it by hand and had a computer do it or something, it would just give me this egg cup that's floating in air. But it's the exact same volume as if you took the same egg cup and lowered it down onto the floor. And it's a lot easier to calculate. Lower this down by 2, actually the formula's easier too. Use that. So the x squared plus 2 you'd never use again. We just lowered it down to y equals x squared, and now spin that. Somebody do the antiderivative for me. Julia Sisha, what's the antiderivative of x cubed?
1/4 x.
Yeah, 1/4 x to the 4th. Do I do plus c or no? Yeah, it doesn't matter in this case, it'll cancel. From 0 to 2. I'm going to pull the 1/4 out in front. What would that make, by the way? What's 2 pi times a 4th? 1/2 pi. You can do pi over 2 or 1/2 pi. And it's going to be x to the 4th evaluated from 0 to 2. Tell me how to do that, John.
So, you just plug it in.
Right, which one first? Yeah.
So 2 first.
So 2 to the
4th.
4th.
Which is 16.
Good.
Minus
0 to the 4th. Yeah, so 16 minus 0, better known as 16. pi over 2 times 16.
It's just 16 pi over 2, which is
8 pi. And that is your answer. Caution. If you had done discs, you would have gotten 8 pi as an answer. But that's the inside volume. This just happens to have the exact same volume inside as outside. That's rare. Yeah.
So, for this problem, I thought we were taking the, like the inside part, but I still used shells, and so I like flipped it over. the
Oh,
X.
oh my goodness.
How did we know?
Wow.
How did we know that we were getting
The outside?
Yeah, the outside and the inside.
Okay. First, if you look at the graph, let me look
Is it
here.
just
Then they
'cause of
see,
the
oh, they
lines?
didn't draw the graph for you, but let me scroll down to number 3. The boundaries they told us were y equals x squared plus 2, y equals 2, and x equals 2. That would surround this area, which is going to give you an outside. If they had said y equals x plus 2, x equals 0, y equals 7, that would have captured the inside.
Okay.
Okay, sure. Any other questions on number 3? All right, any questions on number 4? What was the trick to that one? That's another one that's kind of like a bundt cake that's floating off the floor. This is actually a good life lesson, by the way. If your cake is floating off the floor, fix it. Get an exorcist, whatever it takes, but stop it from floating because that's just wrong. Do you see that's going to be the little bundt, a teeny little bundt cake on the inside, but it's floating 3 spaces off the floor. Number 4, you have to lower that function 3 spaces. It'll become y equals radical x. And then you can spin it around the y-axis and it's pretty easy. Questions? Anybody want to see any of the other ones work? Now's a good chance to ask. Where's that? No. Yeah, that's what I was just talking about. You want to do it?
Yeah.
Okay. Number 4. Somebody go down. I'll try and squeeze here for a little while so people write it down. Everybody tuned in on this and not distracted by other topics. Number 4, because you are going to have to do this on the test. Y equals radical x plus 3, and then y equals 3, and x equals 1. I would immediately graph this, which means you do have to be familiar with what a radical graph looks like. So remember how to graph y equals radical x? Max, talk me through that. Just plain old radical x, how would you graph that?
Well, it looks like the parabola that's on its side.
Yeah, where's the first dot?
0, 0.
0, 0. Where's the next one?
Put one at 1, comma 1.
Yep.
And then, 1, comma negative 1.
That's the entire parabola.
Oh, okay.
That would be if it were plus minus. If it's just plus, you're just going to have the top.
It would be 4, comma 2.
Yes, that's the next one. 4, comma 2, and it goes from there. So over 1, up 1. Over 4, up 2. Over 9, up 3, etc. It's kind of the backward version of the parabola pattern. Now, this does what, Jack?
Raises it 3.
Yeah, so when you graph it, you do the exact same pattern. Start here, it's kind of like starting at 0, only 3 spaces above. Then over 1, up 1. Over 4, up 2. The graph will look like that. Yeah, everybody should be relatively comfortable with graphing that now. That was a pretty power thing. Then graph the line y equals 3. And then graph the line x equals 1. And then look around and see which region got captured. That's this. This little snippet here. And they want to rotate around the y-axis. Did you see the shape you're about to get? You're going to get a phantom side over here. And it's going to spin like this. Now there are 2 shapes in here. There's this kind of bundt cake on the bottom, and then this kind of upside down Hershey's Kiss on the top. We do not want the Hershey's Kiss volume. That's the inside. We want the outside volume. So should I use discs or shells? Here. Explain. Why not discs?
Because you would get an inaccurate line if you use discs.
Why? Because discs normally work perfectly.
Would they find the inside volume?
They find the inside volume. All the if you draw a disc like this, and then go further down, like the best way is pick a random point and let it rotate. That should visually tell you the disc. If you do a bunch of those, it's going to fill into that Hershey's Kiss. It's not gonna fill in the outside. The only thing that can do the outside is shells. If you go shell, so a whole bunch of like empty tin cans, shorter, that'll fill in the outside. I'd love to just do this and be done. What's stopping me? Facts.
Sorry, can you repeat it?
Yeah, gentlemen, do you understand what I just did? Thank you. Tune in. I love to just spin this with shells and do the problem, but something's stopping me. What's wrong? Shells are the right technique to use, but there's something wrong with using shells right now.
Well, it's horizontal. Well, like,
It's spinning this way, so the shells fall down, which is fine.
yeah.
What's
Well,
wrong?
Your graph is this way, not that way.
Now the graph is, the fact that this graph goes sideways doesn't affect our graph here. The shells are fine, they're in the right orientation. You don't have to do the shells sideways. But there's something wrong with just how shells behave.
They fall down.
They fall down, how far?
Till x equals 0.
To the floor, to y equals 0, the x-axis. And if it does that, is that gonna be the right volume?
Yeah.
Let me show you what it looks like. It'll fall all the way down to here.
It'll be too tall.
It'll be way too tall. The volume is way too big. Right. I do not want any of this. I just want this little thing spun. Is there a cure for this? Holly. Yeah, lower the graph by 3. Subtract 3. So we now have y equals radical x. By the way, when you subtract and lower the thing down, it won't always be this beautiful. It might be worse. Because if I started with radical x minus 1, well, you'd have to do plus 1 actually. But there might be some things where there's still garbage here. Just deal. Here, just enjoy the fact that it's next. The new graph is going to look like this. Right here, actually, I might as well just use this. It's going to take this region and spin it. I'm judging whether people are getting distracted again. If the answer is yes. Spin this around the y-axis. Jack, take over. How do you do it? First of all, do you use discs or shells?
Shells.
Shells. So what, if you're doing shells here, what's the volume of a shell?
2 pi r ht.
2 pi r h t. Fill in the missing parts. What's r, what's h, and what's t in our picture?
R is x.
R is x, because the radius is going in the x direction.
H is y.
H is y.
And
The thickness,
thickness is dx.
dx, correct. What's wrong with this formula? Julie, Sean, take over. Yeah, the y. What should we replace it with? Sorry. Yeah. Replace it with the y that we have in the formula, radical x. Can somebody simplify this for me? 2 pi what? John, take over.
X to the 3 halves.
Yes. X radical x would have been fine, but it's not in antiderivative friendly form. This is x to the first times x to the 1/2. So it's x to the 3 halves. dx. Okay, that's the volume of a single shell. Julia Miller, how do you get the whole volume? integral. And are we gonna do an integral, this is actually kind of dumb, it's gonna be from 0 to 1 or 0 to 1, which you can't lose. But are you gonna follow the x's or follow the y's? X's, what tells you that? Two things, too. Yeah, x's are everything, and the dx especially. The dx will command you the direction to go. So from what to what? From 0 to 1. From x equals 0 to x equals 1 of 2 pi x to the 3 halves dx. All right, take over, Max. Take the antiderivative of this thing. What would you do first to make your life easier?
I pull out 2 pi.
Yeah, pull out 2 pi. And then what's the antiderivative of x to the 3 halves?
That would be x to the 5 halves.
Over.
X to 1 half. 2.
How do you do an antiderivative again?
Raise the power of 5 left.
And divide by the new power.
So 5 halves.
Yeah, x to the 5 halves over 5 halves. How do you divide by 5 halves?
Multiplied by 2/5.
Yes, put that in front. 2/5 x to the 5 halves. That'll make it a lot more neat. Can you pull this in front for me?
Yes.
And this is from 0 to 1. Go ahead.
Then you get
Oh, yeah.
4 pi over 5.
Oh, thank you. Oh, no, you're good.
Cameo appearance.
Points for using the word cameo. So it's, I'm sorry, say again?
4 pi over 5.
4 pi over 5, good. And then it is,
X to the 5.
can you tell me what x to the 5 halves is? Put that back in non-friendly form. Well, friendly for us, not friendly for antiderivative. X to the 3 halves is x radical x. What's x to the 5 halves? Good.
X squared,
X squared radical x. Because there's 2 whole x's in here with a half. Now, here it's not too bad, because taking 1 to any power is 1. But if I put the number 4 here, with the number 9 here or something like that, or 49, you'll need this. Because I want an exact, if you type this into a calculator and this were something other than a nice number, you'd get a decimal and I would destroy the points on that problem. Just saying. Letting you know ahead of time. Radical x from 0 to 1. So it's 4 pi over 5. It's going to be 1 squared radical 1 minus 0 squared radical 0. This thing is just 0. This thing is just 1. What's your final answer, Max? First of all, what's the inside?
Oh, that's 1.
It's just 1. Yeah.
So 4 pi over 5.
Yep. And that's it. Does that make sense? Any other questions on 1, 2, 3, or 4? Did I not check off anybody's people who came in? Okay. So 1, 2, 3, and 4. Let me see. Okay. Double check the answers on 3 and 4. They'll be on the video.
Oh my gosh, yeah, we watched Easter in our storage list.
At this point,
Like, we watched Easter in the.
at this point, I hope this doesn't make people nervous, but the book, and to a certain extent I, am now assuming that you're comfortable with doing 5 things. Taking derivatives in general, taking antiderivatives in general, using disks, using shells, and now moving graphs up or down if they're floating. Because you can't have floating graphs when you're spinning. They have to be on the floor when you're using shells. If you're using disks, who cares? If it's floating up on top, they can float all they want. But shells, the reason I can't have a floating graph for shells, the shells want to fall to the floor. And that would make the shells way too big. You'd get the wrong answer. Make sense? Take out your notes, please. I'm gonna try this side. I'm going to take you on a speed course through advanced geometry. You'll have to tell me whether you got this covered in geometry or not. talk a little bit about 3D shapes. For people who had a hard time remembering the volume of a cylinder or the surface area of a cylinder or something like that, this will be your review. Or if you just wanted to see it again. There are two types of things we need to worry about for 3D shapes. Area, and there are two types of area. There's surface area and lateral area. And then the second thing we need to do is volume. Try to write that down. Whenever you have a three-dimensional shape, something that actually takes up physical space and is not flat, you'll have area on the outside and you'll have volume inside. Two different types of area. For example, the different types of 3D shapes. Let's just call this ABC. The first figure is called a prism. What is a prism? Have you heard of that in geometry? What a prism is? What is a prism? Like in your own words. Yeah.
This is like a basic shape, you just extend it and pull back.
Right. In other words, it's basically any polygon extended through space. They're, depending on how much of an artist you are, these can be relatively, this is one of the few things, I cannot draw people to save my life, I do stick figures. But I can actually kind of sort of draw these, so it makes me feel a little better. How do you draw a prism? Draw any polygon you want. Like I'm gonna draw a triangle. It kind of looks like a right triangle, I'm not sure. I don't care. Watch this. Get used to using dotted lines for 3D shapes. Like there's gonna be a side where you can't see, it's on the other side. Do me a favor. From this corner, drop a tiny line segment. From this corner, do an exact same length line segment. Connect it. Now that's actually not a bad 3D shape, although it's kind of hard to tell which side is facing you. Do a dotted segment exact same length from the top one. And then you see the bottom here and the bottom here and the bottom here? Connect them with dotted lines. That's not the best thing. They're supposed to be the same length. This is what we would call a triangular prism. Because it's a triangle extended through space. You can do that with any polygon. You can do it with a hexagon, a decagon, an Aeneaconta, you remember that from way back when?
Okay.
Once upon a time, I showed you how to name all the polygons from 3 to 99. Does anybody remember any of them? Okay. If we have time, like when we come back from break, Easter weekend, I'll show you about that.
Mark, do we get homework at all next week? Because I think next week technically all Solemnities.
Oh yeah, sorry. Basically the rule is if we say the creed at Mass, you don't get homework. So, and we do not say the creed Monday, Tuesday, Wednesday, Thursday, Friday, Easter. Liturgically they're a solemnity, but they're not a holy obligation. What's that?
I think we are actually, at least on Tuesday.
Tuesday they are not. It says in the lectionary, do not, or in the sacramentary epistle, do not, the creed is not said. So.
We're doing like some
Yeah, that's a general rule. So short answer, no, sorry. Yeah. Alrighty, y'all. Waiting. By the way, friendly reminder, only water in this room. Second. Pyramid. pyramid is any prism with one base crushed to a point. Drawing these is a little on the tricky side. Try that same kind of triangle we had before. Now, I didn't do the dotted things because it's hard to tell. Watch this. Go, like, hover, like, near the center of it. Don't put a dot. But hover and go up a sizable amount. Just put a single dot. Now connect every single corner. It's a little better if you rotate it a little bit. This one didn't turn out very well because it's so close to each other. If you had a parallelogram, you could do the same thing. Make sense? Take any shape. It's actually easier if it's not quite so tall. If it's not as tall, it looks better. Does that make sense? We can find the volume of one of these prisms. We can find the volume of a pyramid. We can find the surface area. I need to explain what surface area and lateral area are too. I did briefly before. Surface area is the total outside area. Go ahead and write that down. Surface area is the total outside area. If you take a look at this triangular prism we had here, the side areas is called the lateral area. And then the top and the bottom are called bases. The top base and the bottom base. Make sense? So if you have like a tin can, the top of the tin can and the bottom of the tin can are the bases. Why are they both bases? Because you can tip it upside down and it kind of looks the same. So they can both function as bases. Lateral area is the surface area without the bases. It's just the side area by itself. Lateral means side. So the lateral area is just the side area. The reason we're interested in that is because when we're using shells over here, we're using the lateral area of the cylinder. Yeah, I need your attention. Quiet is great, but attention is better. Does that make sense so far? Let me go through these things. There are certain 3D shapes. There's a prism, there's a pyramid. Oh, I forgot there are two others. Cylinder and cone. A cylinder is a circle extended through space. Go ahead and write that down. And a cone is a cylinder with one base crushed to a point. You may see a strong similarity between cone and pyramid. They are. It's pretty much, a cone is a circular pyramid, if you like. The volume of these things is actually, let me just show you. The volume of a prism. If I use capital B for base area, make a note of that somewhere where you can find it. Like on this triangular prism, you'd have to find the area of the triangle, which is base times side divided by 2. That's the base area. How do you get the volume of a prism? Capital B times H. Tell me what that means. B. base area, whatever the area of the triangle is, times height. Volume of a pyramid. Gentlemen, whatever you're working on that's distracting you, please put it away. Will, if you so kind. The volume of a pyramid is 1/3 base area times height. When you crush something to a point, you reduce its volume to 1/3 of its original. That's always true, whether it's circular or not. The volume of a cylinder is base area times height. It's just a circular base. It's 2 pi RH. And then the volume of a cone is 1/3 base area times height. I'm giving you a lot of formulas. You will not need to know all of these on the test. I'll flag which ones you need. But get them down for now, because they will show up in some of the story problems you have for homework. I think I just have time for this. Area. The surface area of a prism. Can somebody explain what that means? What do you think this means? Decision. 2 times the base. So the area of the top, area of the bottom. So you paint the top, paint the bottom. Area is kind of like how much paint do you need to cover the thing. So the top and the bottom, base and base, plus, what do you think that stands for? The lateral area, the area on the outside. How do you get the lateral area? Take a look. Let me draw this triangular prism again. You don't have to draw it again, just follow along. Question. If I just want the hollow triangle, like just the outer, it's kind of like a fence or a walled in something or other. I want the area of that wall. Does it make sense? Can somebody tell me what's the short term for the distance around that triangle? There's a geometry term for that. You want to try? Perimeter. That's a perimeter. A solid volume is solid triangles stacked on top of each other. Does that make sense? If you have a solid triangle, like a little slice of cheese, triangular cheese, and then stack another one, another one, another one, another one, you get the volume. What if I just want the hollow one? Guess what I'm going to stack on top of each other? Not areas, but what? Perimeters. Perimeter times height. The lateral area is perimeter times height. Let's say the perimeter is 10 inches around, and let's say it's 3 inches high. It's take 3 of those perimeters and stack them on top of each other. 10, 10, 10, to make 30. That's how you get the surface area of a prism. So the lateral area of a prism, we already did, is perimeter times height. Now let's try a cone. Surface area of a cone, or a cylinder rather, first. It's going to be 2b plus the lateral area. How do you get the lateral area? How do you get a hollow cylinder? Pretend this is hollow. How do you get the area of this thing? Okay. 2 pi r. 2 pi r times, what's the next letter in the formula? H. And T is thickness. That'll give you volume. But just 2 pi RH, where'd it come from? Write this down, everybody. Perimeter times height is perimeter, 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 it'll give you a hollow shape. If you have a circular one, what do you call the perimeter of a circle? Circumference. Circumference times height. Which, by the way, is 2 pi r h. Make sense? So the lateral area of a cylinder is circumference times height. That's the one that we use when our shell formula. We give it thickness in order to have some volume. But that's where it comes from. Questions? Okay. If you have all of these formulas, these are key, especially here. The surface area, lateral area. The volumes are good. Oh, here they are. Okay. But these are especially good because later on, like when we come back after Easter weekend, we're going to bring back some of those problems. We're going to have a homework assignment where we have a region where you have a bunch of triangular slices, you have to add them up, or a bunch of semicircle slices, you have to add them up. So for example, I might give you this. Here's a triangle. Super duper easy to get the area. What's the area, by the way? Don't panic about it, but yeah. Half base on side. What's the base? 3. What's the height? 2. So what's the area? 3. So the area is 3. That seems easy. What if somebody told you that these slices going up and down were the bottom of a cake? Like this is just the bottom of the cake, and the cake is semicircular. Find the volume. Each slice is going to be a semicircle. All you have to do is find the radius of this thing. Then you can find the area of the circle, and that kind of solves the problem. The radius in this particular case, or you can do the diameter too, that's fine. Is the diameter x or y? Maybe see it? In this particular picture, what's the diameter of the circle? It's y, going in the y direction. So if you know what y is, and by the way, the equation for this line is y equals 2/3 x plus 0. That's your diameter. Use all these diameters, find the area, you can find the radius from there. Cut it in half, square it, times pi. And then just use an integral to add up all the slices. We're not doing it yet, but we will be doing that in the week we get back. Okay? There is no homework over the weekend, so rejoice, be glad, get some sleep. Nat, is all we have for today. That's not too loud. Let us pray. In the name of the Father, the Son, and the Holy Spirit. Amen. Glory be to the Father, to the Son, and to the Holy Spirit, as it was in the beginning, is now, and ever shall be, world without end. Amen. In the name of the Father, and the Son, and the Holy Spirit. Amen. All righty. See y'all later. This is Bob out the door.
Bye, Michael.